Right guys, welcome to my new video. The sound quality is going to be a bit bad because my microphone doesn't work because I paid £8 for it. You get what you pay for, right? Today's video, as you can see, is going to be about Squid Game. And if you don't know what these symbols are, it means you haven't seen Squid Game. There will be spoilers, so you have been warned. Right, so I was watching episode 7, VIPs, and that involves game 5. You remember the one with the glass tiles, the glass bridge. And I remember thinking at the end that they must have been pretty unlucky to have only the 3 survivors. So it led me to a couple of questions here, 3 questions here. How many people are likely to die / survive on average? Okay. Number 2, what's the likelihood of exactly 3 people surviving? That's what we saw in the show. And then number 3, the players don't behave randomly and well behaved. They mess around and forget and murder people, as you know. So what impact do these actions have on the previous 2 questions? So we're going to get into that now. Model a random variable x as the number of deaths. Okay, pretty gruesome stuff. Now we're going to say, to begin with, that x is a binomial distribution with n equal to 18 because there are 18 tiles, and the probability of dying is a half, okay, because it's a 50-50 choice. This isn't totally accurate, it's very close. When we work out the expectation, we're going to have a slight error. This is because in this distribution, the probability that x is equal to 17 is non-zero, and the probability that x equals 18 is also non-zero, and in fact all of the probabilities are non-zero. But in the real game, there's no way that 17 people could die or 18 people could die because there's only 16 players. So we're going to get a slight error there. I'll show you how to calculate the revised expectation. But if it was a binomial, remember from the binomial, the expectation of x is equal to the number of trials times the probability, which in our case is 9. But we're going to work it out, it's going to be slightly less than 9. Right, so to figure out the actual expected number of deaths, we're going to have to adapt this this random variable slightly, or the distribution of it. We're going to say set x is equal to x1 plus x2. These are 2 random variables. Then we're going to say x1 is the probability of dying on one of the number of deaths on the first 16 tiles. So this is going to be a binomial 16½ because there are 16 players, so every possibility can occur. And then we're going to say x2 is the number of deaths on the last 2 tiles. That's going to depend on x1. So we're going to draw a probability tree. This is x1. Now x1 can either be less than or equal to 14, thus allowing 2 players to live on to do the last 2 tiles, or x1 can equal 15, or x1 can equal 16, and these then subsequent probabilities will be different. So then we draw the next branches. We have x2 can equal 0, or x2 can equal 1, or x2 can equal 2, and that's on all 3 branches here. x2 equals 2. So the probability, if there are 2 survivors, x2 will be another binomial distribution with 2 n equals 2, so this will give us a quarter chance of that happening, a half chance of that happening, or a quarter per chance of that happening. If x1 equals 15, that's only one player. There's a quarter chance he doesn't die, and there's a 3/4 chance he does die, and there's 0 chance that 2 players can die because there's only 1 player. And here again, if all 16 players are dead, x2 will 100% be 0, so that's a 1 probability and a 0 probability and 0 probability. So to find the expectation, we want the expectation of x. Well, that's equal to the expectation of x1 plus x2. I was getting ahead of myself. which we can split up because expectation always behaves nicely. Now we know x1 is a 16½ distribution, so it's 8. The expectation of that is 8 plus, and then we have to work out all these probabilities using joint probabilities. We get, it's well, let's do it down here. We have a quarter, 0 times the probability that x2 equals 0, plus 1 times the probability that x2 equals 1, plus 2 times the probability that x2 equals 2. And these probabilities, you work them out, you multiply that by that, plus that times that, plus that times that, to give you this. And similarly, that times that. It's a faff. You get the answer is equal to, where is it? I've written it down. 8.999927. Sorry, 0.9927. We add it to here. So we get our overall expectation of x is equal to 8.999927. Virtually 9, right? A lot of work for very little payoff. So there is an easier way to work this out, but I'm not going to tell you how to do it. I'll let you have a little think about it and have a go. It's a bit easier. This is the answer to the second question. If everybody behaves normally, what is the probability of 3 survivors? That's equal to 13 people dying. And this is just come straight out. We put it into our binomial formula. 1 over 2 to the 13 times 1 over 2 to the 5. So that's 1 over 2 to the 18. That comes out at roughly 3.3%, or 1 in 30. So if everyone behaves normally, it's a reasonable chance of 3 people surviving. Not great, but not beyond the realm of possibility, right? As you remember in the show, it doesn't all go smoothly. They all misbehave, or some of them do. There are 3 things that mainly have an impact on the number of deaths that I thought of. So the first thing we have is player 4. He's not paying attention when player 3 makes a run for it, and he forgets the next tile. So what impact is that going to have? Then we have player 9. Doesn't want to go, so he forces player 10, throws him off the side, and then player 11 grabs him around the waist and kills him. And then player 13 can tear the glass apart until the front man turns off the lights. So what impact is that going to have? So we're going to explore them, not with probability trees, you'll be glad to hear. I used a bit of Python to run a Monte Carlo simulation, which I will show you now. First one, I'll pop it up on the screen. This is just the standard everyone behaves, just to check that the simulation was working okay. And as you can see, yep, we got slightly more chance of 16 deaths than 2, so it's not exactly symmetric, and of course 0 chance of 17 or 18 deaths. But other than that, yeah, it looks pretty much like a standard binomial with the results we already worked out. We're going to look at each situation in isolation to begin with, before I add them all together at the end. So this is the graph with player 4 forgetting the next step, and as you can see, it effectively adds another pair of tiles to the end of the bridge, because he has to redo that one. Now if you see, the mean is not quite 9.5, it's a little bit under. That's because if the first 3 players all died, he wouldn't have a chance to forget, because the tiles in front of him will be broken. So it doesn't increase as much as you would first think, but it does increase a lot by, well, effectively half a tile. And it also increases the probability that we just see 3 survivors. They haven't increased their probability of surviving in total, but the probability of exactly 3 survivors has increased a little bit, just because the entire graph has been shifted to the right that little bit. Here we have probably the most interesting one. This is where player 9 doesn't want to go. He throws player 10 off the side and player 11 kills him. Now I assumed in the simulation that whether or not the glass tile broke under 11 and 9, they would have struggled around and died anyway. So it's not like they can keep adding information for the rest of the group to use. And what we see here is there can be no deaths. There can't be 9 deaths and there can't be 10 deaths. And I thought there couldn't have been 8 deaths either, because as soon as player 8 dies, 9 then acts and then does. That's a foregone conclusion. But I didn't consider the scenario where player 8 dies on the last tile, in which case 9 wouldn't panic, wouldn't kill anyone, and they would all make it to safety. So the chance of that happening is going to be yet another binomial distribution. So it's the chance that 7 people die on the first 17 tiles, which is that, and then player 8 has to die on the last tile. So that's a probability of a half happening. And then if we work that out, we get, let me just check, 7.4%. And that's where that little bar comes on the 8 deaths. Okay. So lastly, we look at player 13. He gives 3 tiles of information to the following players and himself. So you would think that would decrease the expectation by 1.5 on the number of deaths, but in fact it only, as you can see on the graph, reduces it ever so slightly. And the reason for that is because he acts so late. He's player 13. If he had been player 1 or 2, it would have had a bigger impact for sure. You can have a play around with the code and see what difference that makes. And the probability that 13 people die, therefore we only have our 3 survivors, has dropped now to 0.32%. Now that doesn't mean that their probability has gone down. In fact, it's gone up. It just means that it's very unlikely that we'll have only 3 survivors. We'll probably have a lot more, okay, because of this extra boost that player 13 gives us. Lastly, not much to say here. You can see the first 2 people's actions. This is all 3 together. So player 4 and player 9 doing what they do has pushed everything to the right, the right. And then player 13 has pulled everything to the left. So it's bunched up at 12 deaths is the most likely by far number of deaths. But it does show us that the probability of 13 deaths is around about 9%. So that's a 1 in 11. So what we saw in the show is absolutely believable. Okay. And that's pretty much it. The only thing I want to add is, of course, at the beginning of the game, when you've got all of them looking at the bridge and they understand the rules, the first 9 players, which would have been a majority, should have gone, hey, listen, we're not playing this, there's a good chance we're going to die, right? So they should have had a vote and then all gone home. But hey, it wouldn't have been much fun to watch. Right, so I hope you enjoyed it, and I'll see you next time.